Who wants to come up and try to classify one as aromatic, anti-aromatic, or non-aromatic?
I'll try.
She always volunteers. I'm glad you put up.
It's the one thing I know, because I didn't read anything yet. So, that's SB2, that's SB2, so are those, that's not SB2.
It is sp2.
What?
Carbocation, always sp2. It's got a bond, so it's still got one hydrogen, right? And then it's bonded to two other carbons. So if it's bonded to three things, sp, p, so sp2.
Yep.
That's three, yeah.
And then it's got this plus charge going on. So that just counts as yeah, because this is all SB2.
Yeah, so they're all sp2, so are you saying it's aromatic?
Yeah.
So remember that there's a numerical rule
Oh yeah.
figuring out if something's aromatic, because it could be anti-aromatic, depending on how many electrons it has.
So 4 times number of carbons? I don't know,
The number of carbons factors in. I think it's number of delocalized electrons is in there.
Is it? Wait. What's the equation, guys?
Yeah, someone needs to.
I got it. Is that it?
Like odd number of pairs of electrons.
Odd number pair.
Yeah, it's odd numbers of pairs, but I don't know the
Odd numbers of pairs. Okay.
That was like 4n plus 2.
And it's
4n plus 2.
I got that. But what's the n part of it in this equation?
Well, it could be anything. It could be 0, it could be 1, it could be 2. I think it has to at least be 1. So if n was 1, it would be 4 times 1 plus 2 is 6. So aromatic could have 6 electrons.
Yes.
If n was 2, it would be 4 times 2 is 8, plus 2 is 10, so it could have 6, it could have 10, it could have 14. You can pretty much start at 6 and keep adding 4. But this has how many delocalized electrons?
None?
That's not true.
I don't know.
So
Explain that.
these could go here and make that positive charge happy, right? But then we put the positive charge here. And then these could make that positive charge happy, but that would put the positive charge here. How many electrons are moving around when it does that? 4. Yeah. So it's got 4 electrons. So it's not aromatic. Is it anti-aromatic?
16, 18.
Alright, so as long as it meets those first two, that's what's called Huckel's rule. That's the 4 plus 2 thing.
Wait, why doesn't 18 work? If it's 4, 16, 18. Yeah, so, but you just said it's not aromatic.
It doesn't have 18.
It does. Wait, you just said there was 4
Right.
delocalized electrons.
No. 4 isn't what you plug in for the n.
What
If
do you
you
plug
plug
in
in
for
the
the
number
n?
of electrons here, you'll always satisfy that rule.
Okay,
It's saying
what
if,
goes in there
if
then?
n, just any number.
Any?
As long as n is a whole number, like 1, 2, 3, 4, as long as your number of electrons meets one of those numbers, then it's aromatic. So if n is, like I was saying, if n is 1, it's 6, then it's 2, it's 10, then it's 3.
I think what she's asking now is whether the n stands for the number of electrons.
No.
Or the number of pairs or something.
No, it doesn't actually stand for anything. It's just saying that any number that meets this formula, so 4n plus 2 equals some number,
Yeah.
regardless of what n is, as long as it's a whole number integer, so 1, 2, 3, 4, 5, like that.
When would it not be a whole number?
Never. That's what I'm saying, is anything that meets the rule where n is a whole number, 1, 2, 3, 4, 5, whatever number you get out of that are numbers of delocalized electrons you could have that would define it as aromatic. So the numbers that fit this are 6, 10,
Oh, and it has
14,
4 delocalized electrons?
18, right, so it's not one of these numbers, so it doesn't work. So you can just, and I guess if n was,
Okay.
if n is 0, it's 2, but I don't believe 2 delocalized electrons gives you aromatic. So I'm pretty sure is just 6, and anything where you can add 4 to 6. If you have that number, any of those numbers, it counts as.
Okay.
That make sense to everybody? It's just kind of giving us a number set that says that these numbers of the localized electrons constitute as being aromatic. So
basically any double bond is a 2 electrons.
yeah.
So they didn't have the plus charge because they both leave the localized.
Technically, they could, but they wouldn't actually be localized, like move between 2 more carbons. You could just like move the pair of electrons on the carbon, create a plus and minus charge, but that's just contradiction. Yeah. But this does mean that it's, so that would be non-aromatic. If you didn't have that plus charge, it would be non-aromatic. But yeah, this makes it so anything that meets the first 2 criteria, like you said, it's planar, sp2, but it doesn't meet Huckel's rule, so that makes this anti-aromatic. Anybody want to come up and do another one?
If that was a minus, would it be then? When it would have 6?
Well, that's drawn somewhere up here, isn't it? I thought I drew that.
Oh, yeah, it is.
Oh, it's supposed to be right there. Thank you. Oh,
Yeah.
never mind. Okay, you want to come up and do that one? Get up here. Come up.
Why is it anti?
Because it meets the first 2 criteria of aromaticity, but it doesn't meet Huckel's rule, which is the 4n plus 2 thing.
Ah.
So, like you said, it's sp2 all the way around, and it's got these delocalized electrons and everything. It's planar, right? Because planar comes from it being sp2 all the way around. So it's got delocalized electrons, and it's planar, but it doesn't meet Huckel's rule. So
Okay,
so that's anti-aromatic. Non-aromatic is it's not even, it doesn't meet one of the first 2 criteria. If it's not planar, if it doesn't have the delocalized electrons, it can't be either. But, so this is anti-aromatic. It's almost aromatic, but it doesn't meet that. So anybody? No volunteer? No?
Don't embarrass yourself, guys.
Come on. Somebody. I'll call on someone again.
Sorry, the benzene ring with CH2 and positive charge on the C, that's aromatic.
Yeah, because you've got 2, 4, 6 delocalized electrons, which is one of the things that meets Huckel's rule. Also, since this is positive, it's planar all the way around, so you can have the electrons going into here as well. So that would make this aromatic. Right. So you guys would rather just call out and have me write what you say? Does that work better for everybody? Yeah? Okay.
I'm confused on how that one's
Alright.
because in the book it says the cloud must contain an odd number of pairs of pi electrons.
Alright, so how many pairs of pi electrons does that have? Well, there's one here, right? That's pi. Double bond always has a pair of pi electrons. That's pi. That's pi. Does anything else have a double bond? Does anything else using pi electrons? So we got 3 pairs. 3 is an odd number.
Do it on that list.
Yeah. So I think that's actually where this whole thing comes from. Because if you had 3 pairs of electrons, it would give you 6. If you had 5, it would be 10. If you had 7, it would be 14. So these are all just odd pairs doubled. So that's why it's 4n plus 2. Because the 4n gives you even pairs, and the 2 makes it odd by adding another one. So that's where that actually comes from. Yeah, you could also look at it odd number of pairs. So this is the same thing as Huckel's rule, that odd number of pairs.
That one's non.
That one?
Yeah.
Why?
Because it's got like an SPP
Where?
at the bottom.
Right there?
Yeah.
Yep. Non-aromatic. Anybody? Nobody's gonna come up here? Come on. We're all friends now. Alright. What about that one? People can just start shouting.
Non.
Why?
Because the SPP
SP3s? Where are SP3s? I don't see any SP3s. No, I see some SP3s. Yeah. So right there, we got SP3 carbons, right? 4 bonds. So that makes this non-aromatic. So I got a question for you. If we had something like this, is that aromatic? Oh. Yeah, that's correct. But is that aromatic?
But that's not.
That is aromatic, though. So just because there is an SP3 doesn't mean it's not aromatic. As long as the SP3 is outside a potential, aromatic system. So in this case, if we had another double bond here, then we'd have these electrons flowing like in a benzene ring. That would make it aromatic. But because these two can't accept them, it makes it so it's non-aromatic. But in this case, that methyl group has no bearing on this benzene ring. That benzene ring is definitely still aromatic. It's still got the electrons moving around, right? It's got 3 pairs. So this one kind of is confusing because it makes you think, well, this is just aromatic because of that positive charge. It's not. Anything stuck to a benzene ring, the benzene ring is still aromatic. So.
Care about the things attached to the benzene?
No.
I think the difference is with that one benzene ring or the CH2 onto it, is that you've got the 3 double bonds, and it's in a benzene ring, so it's planar. It's got sp2 carbons. The other thing about the CH2 with the positive charge is that you could actually have some delocalization onto that carbon.
So that adds a lot of stability to this position for the positive charge, right? Because the electrons can jump up there. But that isn't what's making it aromatic. The benzene ring is what makes it aromatic. This just actually enlarges the size of the aromatic system because now the aromatic electrons can go up there and then come back out.
Right, and with that other benzene ring with the CH3, the electrons stay delocalized within that ring system.
Yeah, just in the ring. So this one isn't involved with the aromaticity at all, but this molecule as a whole is still aromatic because it's got an aromatic system with benzene. So in this case, you never have a complete aromatic system, right?
That's true,
but it does have some conjugated double bonds. It's just like in this case, you can kind of move this all the way around the ring if you think about it. These electrons can go all the way in a circle, so you kind of need a way for them to get around. And that one doesn't have that because they can just kind of go back and forth this way. You can't really do much else. And they really don't have anything like, you've got the delocalization of charge because of the conjugation, but that's it. You don't actually have something like this where the electrons are like, they have that diagram where it shows like the two, like they look like bicycle wheels that's on either side of the benzene ring, and the electrons are just sort of chilling in those rings going around in circles. You guys know what I'm talking about? It's in the book. It's right there.
Oh, okay.
So it kind of shows these two are holding. Yeah. So this doesn't have that because it doesn't have those empty p orbitals on these guys that can accept electrons into them. So it's kind of like there's been a big slice taken out of your bicycle wheels so you can't ride.
Okay, so the difference between the anti and the non-aromatics, it was between that first one and that pizza slice over there. You still have delocalization, but the anti actually has places for the double bonds to kind of move around too.
Yeah.
But with the pizza slice, it really can't move around without breaking something off.
Yeah, so essentially you always need an aromatic system to be aromatic or anti-aromatic. So these electrons can go all the way around, these electrons can go all the way around. But it just comes down to how many pairs of delocalized electrons you have that determine whether it's anti-aromatic and aromatic. It's the only difference between those two.
So if anything has to fall off for everything to go around, then it's not aromatic.
Yep. There you go. So, what about this one? one's actually
Oh, wait.
this one's actually really confusing. I hate this example because it confuses everyone. It's that great thing that's in every concept in chemistry where it's like, oh, you're finally starting to get the hang of this. Now look at this exception that you would have never considered. This is actually non-aromatic just because it's not planar technically.
Why would it not be planar?
Because for the bond angles, since these are sp2, they like 120 degree bond angles, but when you start putting things in a stop sign shape like that, that is not a 120 degree angle,
Even though it's sp2?
even though it's sp2.
So does that widen the bond, or does it?
Well, that's the thing, is it trying to be in that flat shape
Uh-huh.
with 8 carbons, it's trying to widen the bond, but sp2 carbons like to have 120 degree angles.
Right.
So it actually buckles and forms
Oh.
this thing, kind of like folded up box.
Right, okay.
And you've got double bonds here, 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 and here. It's called the buckled shape, and that's so that these sp2 carbons can get their 120 degree bond angles, and that makes it so it's not planar, so it's not aromatic.
Okay.
That example, awful. Because every time like an OChem student starts to feel like, I start to get this now, it's like, oh, but what if this happens? That's the only example where something like that happens. You never have to consider that.
Okay.
It's pretty much just one of those things you just need to know that like 1, 3, 5, 7 cyclooctatetraene is non-aromatic just because that.
So if it's just bigger than
So does that have, is there like a certain number of carbons where it starts doing that? I mean, it does it with the 8.
After 7.
After 7.
Anything after 7, it's too much, so it starts to do what's called buckling.
Okay.
So that it's called. So it stops being planar.
Okay, so, but it's 7 and after?
Yeah, and that's in one single ring. So if you have something like this.
Oh, so if you have like 2 rings together, it
Yeah. Oh, now we can make that
so if one
cyclopentane
ring
one
is
out.
bigger than a cyclohexane, so that doesn't work. If it's bigger than that, it
Yeah,
would-
exactly. So like in something like this, if it was conjugated,
that wouldn't work.
that's still fine because since this is a 6-membered ring, 6-membered ring, 5-membered ring, it's still conjugated. Does that make sense? We're all good on that? Awesome. So yes, the one with 8 carbons, you just sort of have to know that once you get beyond that point, like maybe he'll give you an example that has like 10 carbons, and you can just,
And you already know it's buckled.
Yeah. because anything after that, the buckling actually starts to look kind of cool when you get pretty high up. So that was also my own example. Let's see. So we're halfway through. All right. What about this one?
Sure, yeah.
How do you know if this one has a part of it, not?
You have to be able to decide if they can go anywhere. So you have to decide if they're delocalized.
Could they be delocalized because they're inside of it?
Technically, yeah. So this one could go onto that carbon, and then this could go onto that carbon. So you could get like a minus charge here, and then your nitrogen with 4 bonds would have the plus charge. So technically, yeah, they're delocalized.
And how do you know if it's in the on the outside, but somehow like they can be delocalized? Like, I'm just worried.
What do you mean on the outside?
Like that.
Like drawn on the outside?
Yeah. Like
Oh yeah, that does. Like this versus that?
Okay.
No, that doesn't make a difference. It's just I arbitrarily drew a pair of electrons here versus there, but I'm just showing they're on the nitrogen.
Those can still be delocalized. Like I'm just saying, like there's the
These?
same problem, but without the hydrogen.
I don't know if those could be delocalized because that nitrogen's in a double bond.
Well, not for that problem, but I'm saying like
On that one?
this problem, like without the hydrogen, like you don't have to be on the outside, would those be
Yeah.
delocalized? Okay.
Yeah. But if it didn't have a hydrogen, it would probably have a double bond already. So in that case, they wouldn't be. But yeah, if you just had like nitrogen bonded to something else down here, I guess, like another ring, then yeah, they would still be delocalized. But I'm not sure I completely understand what you're asking. where you draw the electrons doesn't affect whether they can delocalize or not. But I did draw the electrons on top because that hydrogen's there. The fact that that hydrogen's there means that this nitrogen's only in single bonds here, which does contribute to the fact that it can form this double bond in the resonance. It's already got a double bond, it can't form like another double bond in the resonance, if that makes sense. I think that makes sense. So what would that one be? Aromatic? So the thing about aromaticity,
So it would get stopped. So it can't go all the way
would,
down.
exactly. So the way you can kind of think about it is that if you ever have to put charges on it because of the movement of electrons, then it's probably not aromatic. Like charges that weren't already there. In a case like this, there was already a charge there. But in this case, there's no charges, all the carbons, the nitrogen, they're all happy, they're fine. But if you start moving around the delocalized electrons, you get negative charges up here and positive charges down here. Once you start,
separation of charges.
yeah, separation of charge, not aromatic. So that's what I meant by it has to be able to continually move around. If it can't continually move around, then that means you're going to end up with a separation of charge at some point. So like that technically has 6. It's got 3 pairs of delocalized electrons, but it's not aromatic because eventually you're just going to have to stick one of those electron pairs on a carbon and make a negative charge. So, when you look at that, you wouldn't think aromatic, right?
Well, right, because it's not aromatic.
Exactly. So, this is kind of the same situation as...
Oh, yeah, it is.
Yeah, it's just stuck together. But since you would have to create a separation of charge, that's why the delocalized electron system isn't considered aromatic.
Okay.
So this one would be non-aromatic. What about on that one? Yep. That one. There you go. Yep. So we're not going to create any new charges by moving that around. So that makes it so we don't technically have a separation of charge because we're always just going to have a carbanion on one of these carbons as they move around. So they can continually keep going. What about this one?
They might be aromatic because they could just switch positions.
Yep.
Because there's lone pairs on.
And this one? It is. So 2 is fine. If n equals 0, you get 2. That's 1 pair. It's an odd number. So this is aromatic because you can move these electrons there or there to satisfy that positive charge, which would put one here, and it would keep moving around like that and moving the positive charge. So it's got 1 pair delocalized, so it is aromatic.
But that 4n plus 2, so that's like the number of pairs of electrons?
No, that's the number of actual electrons.
Number of electrons?
Yeah, so you can either do it by pairs or you can do it by actual electrons.
Yeah, you can do 2n plus 1 a number of pairs if that's easier to think about.
But when would it be like 4 and n is 0?
So if n was 0, 4 times 0 is 0 plus 2 is 2. That means we have 2 delocalized electrons. That has 2 delocalized electrons. It's 2. So that's the case where n equals 2.
Those are like 2 pi electrons.
This is a case where n equals 1. And we didn't have a case where n equals more than that, but you can. Like if you had 2 benzene rings stuck together, you would draw it like this. And it kind of seems like there's only 2 pairs in that, benzene ring, but that's because technically if you draw the resonance, let's draw it like this. It kind of shares one between both of those. So that has 5 pairs. So that's the case where it's 10. So that's where n equals 3. Oh, wait. That's where n equals 2, sorry. And then n equals 3, you could keep sticking on benzene rings to that. Now n equals 3. Another one would be n equals 4, because you would have 18 electrons, or 9 pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9. Like that. Does that make sense? Or did I just confuse everybody?
When it's 4n plus 2, the n is the number of delocalized electrons, and if it's 2n plus 2.
No. 4n plus 2 equals the number of delocalized
Oh, it
electrons.
has to be.
N is just some random number. It doesn't matter what n is. The number of delocalized electrons just has to fit a scenario where n is either 0 or 1 or 2. So 4n plus 2, the numbers that could produce if n was 0, 1, 2 is 2, 6, 10, 14, 18. Those are the numbers of delocalized electrons you want.
So I figure out which ones are localized electrons.
If they can move around. So that if they were localized, they'd just stay where they were. They'd be a local. Go. If they're delocal, that means they're moving around. They like to travel.
They move maybe like a little bit, not like all the way around.
No, they're just spinning in their element, so that makes them delocalized. Every electron's delocalized. Everything you're learning is wrong. No. So even if you get the separation of charge situation where you've got a conjugated system that's delocalized electrons, doesn't imply aromaticity though, like with the hexane chain with the 3 double bonds I showed earlier. You have to have that delocalized electron system in a planar molecule, or at least the part that's aromatic has to be planar, without a separation of charge. And then after you have those things, you can look, does it meet Huckel's rule? If it does, it's aromatic. If it doesn't, it's anti-aromatic. Anti-aromatic means it met all those other criteria before. So we all good now? We all understand that? So he mentioned you guys are going to be doing multi-step synthesis.